Okay, let's see here. We are on evidence for evolution. We're looking at explore number 4. And the essential question we're looking to answer is how do molecular sequences provide evidence for evolution? Go and write that down. Put your date, put your reference, 3.5.4, and hit the pause button. Tell me what you know. Tell me what you think. All right, and give it your best shot. Okay, well, hopefully you took a moment to tell me what you think about molecular sequences providing evidence for evolution. And the first thing we're going to do, Roman numeral 1, go ahead and write down homologies. Remember, we've been talking about similarities in body structure, right? Homologous traits we've been looking at. Well, are there homologies at the genetic level? You know, it's one thing to say, oh, yeah, look at the arm bone of a mammal, line up 4 or 5 different mammals, and you can say that there are homologies in the bones. All of them have humeruses, all of them have radius, all of them have ulna bones. But can we go to a deeper level? Can we take a look at the DNA and see that there's homologies at the genetic level? Right? So obviously this is going to require looking at molecular sequencing. So a couple examples that your text starts off to introduce this idea. They point out the protein cytochrome C. It's a protein which we have. In fact, most animals have a very similar protein in it's all used for the same thing. It's all used for cellular respiration. Um, so, of course, does this provide evidence for a common ancestry? The fact that all living things appear to be using the same protein to execute cellular respiration? Well, you can't ignore it, right? It's a piece of evidence, and it has some weight to it. The second example they provide genes that code for ribosomal units used in protein synthesis. Remember, uh, your you have your messenger RNA, you have your tRNA, you have your rRNA. These are different ribosomal units that are responsible for doing your transcription and translation when you are copying your DNA, when you're trying to decode a certain segment of your genes to manufacture a certain protein, um, you have to use your ribosomal units. Well, the interesting thing here is that uh, the hardware that we use is no different than the hardware that the bacteria use. Bacteria and eukaryotes share the same genes that code for these ribosomal units. That's interesting. You have to pause and ask yourself, is this just chance? Is this coincidence? Or does this indicate that maybe we, in fact, came from a common ancestor? And that's why we see these different organisms today using the same genetic code to produce these ribosomal units. And again, it it can't be ignored. It's something that has to be contemplated, right? It likely is due to a common ancestry. Letter C, we can compare the genetic sequences in DNA for protein and for proteins. So we can compare the gene sequences to determine how related organisms are. In fact, that's what we just did talking about A and B there, right? When you compare genetic sequences, this is no different than you comparing the bones in your forearm, in your arm, right, or in your hand, and saying, "Wow, these are the same bones." Well, it's a similar sort of thing when you take a look at things at the genetic level. The interesting thing here, I've got in red, the greater the number of differences, right? The greater the number of differences, we're talking about in a gene, right? You got all those A, T's, and C's and G's. The greater the amount of time that has elapsed since having a common ancestor. If you have only a few differences between you and another organism that you're comparing, then likely you're fairly closely related. You have very few mutations between you and the other organism. If, on the other hand, you're comparing yourself to an organism, you're comparing a stretch of DNA, and you see that there are quite a few mutations that have occurred, then you can infer that a relatively long period of time has probably occurred since you both had that last common ancestor. And that brings us into this whole idea of molecular clocks. Roman numeral 2. And we're going to take a look here. Okay, so what are molecular clocks? You know that a clock is something we can use to tell time. It's something we can use to time things, right? Stopwatches. It's something we can use to count down a period of time. So a molecular clock is really a similar sort of idea. These are techniques that we use. You have a lot of genes on a chromosome, and all those genes have different mutation rates. You know, they don't stay perfect forever. They tend to mutate. And sometimes they have a fast mutation rate, sometimes they have a slow mutation rate. For example, if you have a mutation rate of one base per million years, if you have two mutations that have occurred, then you can infer that 2 million years have passed since a common ancestor. And these molecular clocks are super useful when you're comparing yourself to another organism. You compare a similar gene, and if you know the mutation rate for that gene, you can infer based on how many mutations you have compared to the other organism, you can infer how long ago you guys shared a common ancestor. That's pretty interesting, and that I encourage you to think about that. This is probably one of the more challenging concepts you're going to encounter, but it's very valuable. So letter A, we kind of already talked about that. Different genes have different mutation rates. This can allow us to figure out how much time has elapsed between you and another organism. And in red, you can see I've kind of put a star there. If you know that a stretch of DNA changes by one base pair per a unit of time, whether that's a million years or 10 million years, you can figure out how long ago you and another species diverged from a common ancestor. All right. Well, I think that it's going to be really valuable for you to watch the videos on this. Okay. You got this molecular clock video here, and you have this molecular comparison video over here. So we'll talk about it a little bit more in class. Make sure you spend a little bit of time and contemplate this. Go ahead and make sure you write your summary paragraph, and we'll talk to you soon.